First thing we're going to do is we're going to, I'm going to go into just a very brief introduction to what analysis of variance is and how it's kind of similar to the t-test and how it's different from the t-test. Okay, then we're going to kind of launch into an actual demonstration of SPSS using, of analysis of variance using a series of 4 demonstration videos. I call them lab here, but they're more demonstration videos necessarily than a lab session. Although the data sets are here. If you want to download the data sets and follow along with the videos, or work on your own afterwards and just really not work on your own, you can do that. And I know I'm repeating myself, but I want to make sure we get it recorded. The first video is basically an introduction to the concept of analysis of variance. The second video, and these are all like about 5 or 10 minutes long. The second video, it takes 3 very simple data sets, 3 groups that we have a numerical variable for, a test score, for instance, and it analyzes whether the means of those 3 groups are the same or different. Okay, in fact, we're trying to show that they're different. Okay, the numbers are very simple. They're just integers, very simple numbers, very small data sets, but I think they're a good demonstration of how the calculation for analysis of variance is performed. Let me stop that. I inadvertently started that. The third video is the same data set analyzed with the same analysis using SPSS. Obviously, much faster, much more accurate, much less likely to be prone to errors, calculation errors, and so on. Okay, and the fourth video is an extension of analysis of variance that's called a series of post hoc tests. Post hoc means after the fact. So they're tests that you can run after you complete analysis of variance, and by the time we get to that point, we'll understand why we need those post hoc tests and when it's appropriate to run them. And then after we're done with all that, I'll go through a PowerPoint on analysis of variance so that we make sure we cover the assumptions that have to be made for this to work, and the rules that we need to follow to make sure that we're not making a mistake with analysis of variance. We're not running it incorrectly. Okay, so I'm going to get started first. And so let me just get something I can sketch with, and so on and so forth. So when we do the t-test, right, we learned that the t-test was a way for us to compare the means of one group to the means of another group, right? Could be males and females, could be math students and liberal arts students, could be diabetics and non-diabetics, but we're dealing with numerical variable, right? Numbers, scores, numbers, blood pressure, BMI, and so on and so forth. We're dealing with numerical variables. So with numerical variables, when we take a sample, we calculate the mean of that sample. We also calculate the standard deviation of that sample. Of course, as always, we're really interested in the means of the samples and the standard deviation, means of the population and the standard deviation of the population. But this is typically our only window on what those are like. The mean, the mean of the sample approximates the mean of the population, and the standard deviation of the population, sigma, approximates the standard deviation of the sample approximates the standard deviation of the population. So we're doing this so that we can get a window on that population. When we have 2 populations, we're very frequently interested in whether the mean of one population is equal to the mean of the other. So for instance, if we wanted to know if we wanted to compare the BMI, which is a numerical variable, for diabetics or not diabetics, right? Well, we would calculate, we'd sample population and determine which ones were diabetic, which ones were not diabetic, and then we would have a list of diabetics that, for instance, we would have the BMI for 26.2, 31.0, 24.1, and so on and so forth. And the same thing for people who are non-diabetics, 22.1, 23.2, 25.1. So we sample those populations. then in order to compare whether there is a difference in the BMI for people who are diabetic versus people who are not diabetic, what we would do then is we would calculate, add them up, divide by the number of people that we sampled in our random sample, and we would find the average for people who are diabetics. Then we would compare it to the average for people who are not diabetics, right? And we'd say to ourselves, okay, let's say this came out to be 25.3 and this came out to be 23.2. Well, now our next concern would be, well, can I extrapolate from the sample and say that indeed the mean for diabetics, mean BMI for diabetics, and the mean BMI for non-diabetics, that those two are equal, or are they different? They're not equal, right? And that's our hypothesis, right? Mean non-diabetics. Okay, so that's really what we're looking for here. We're really interested in the population means, right? But unfortunately, we don't have access to them, so we're stuck with the sample means. So now we have them, we've calculated them, right? So how do we know if this is different enough that we wouldn't get this result just due to chance? Obviously, if I sample 25 diabetics, 25 non-diabetics, right? Say sample sizes just happen to be the same, they don't have to be. In this case, they're the same. Okay, let's say I sample 25 of these and 25 of these, and the mean comes out 25.3 and 23. Well, we know that if I sampled diabetics again, if I sample another random sample of diabetics, and we sample 25 of them, nothing says I'm going to get exactly 25.3 again. I might get 24.2, or I might get 27.1. I really don't know what, if I sample again, what I might get. I do have a clue though, don't I? The clue is if these numbers are very variable, they're very different, very high and very low, big difference between them, and the big difference between them and the mean, I know that the variability, sigma for the population and standard deviation for the sample, that the variability in this group is very large. So that means I can't trust this quite as much as I could if these numbers were very close together, if they were 25.1, 25.4, 25.2, 25.0, 25.2. In other words, if they're very close together, I would have much greater confidence that this number really represents something that's close to the population mean. And the same thing here. So if I don't have a whole lot of confidence that these numbers could be considered, that might not be considerably different, then it's hard for me to be sure that I can say that they're not equal, reject the null hypothesis, and accept that the alternate that they are equal. In other words, I need evidence to tell me that I can be at least 95% certain that these numbers are so far apart that I can be sure, 95% certain, that if I reject the null hypothesis, say that they're different, that they're different, that I might not be wrong. Or, in other words, that 95% certain that I can reject, or I can also phrase it this way: less than 5% chance that I might be wrong, or in other words, alpha error, our probability of being wrong if we reject the null hypothesis. Our alpha error is less than 5%. That's that p-value of 0.05. So these two things go together: 95% certain that you're right, along with less than 5% chance that certainty that you're wrong. So we're looking at it both ways. In statistics, we usually look at this alpha rather than the level of confidence that they're different. Okay, so that's really what we're after when we do the t-test. And the way that we manage to do that is, instead of looking at it from the perspective that the mean 25 is different from the mean 23 by how much? 25.3, 23.2, 1, there's a difference of 2.1. So instead of looking at it from the perspective of what the numerical difference is between the two averages, we look at it from the perspective of how many standard deviations apart are these two numbers. Not 2.1, but how many standard deviations apart are they? Okay, not BMI numbers, but actual standard deviations. Well, in this case, since we're comparing two samples, that standard deviation, not really a standard deviation, It's the standard error. It's the performance of samples drawn from these two populations. How variable are repeated samples from these two populations? And that's specific for the sample size that we've taken from the populations. Okay, sample size for the first population and a sample size for the second population. Well, the standard error, and that's based on the standard deviation, really it's based on standard deviation of the population divided by the square root of the sample size, but we never know that. So it's really associated with standard deviation of the sample divided by the square root of the sample size, right? Well, we got a little bit of a problem here. We have two samples. So which of these two samples do we use to determine what standard deviation that we would use when we calculate standard deviation of this of each of these two samples, right? Well, what we do is we take a composite of both samples. In one case, we might assume, for instance, and it's based on what we actually calculate standard deviation to be, we might assume that the two standard deviations are equal, or standard deviations of populations are approximately equal. Or we might assume that the standard deviations are not equal, that they're different, that one of these is more variable, significantly more variable than the other. Well, functionally, the way that we do that when we calculate manually is we say if one of these standard deviations is twice the standard deviation of the other group, then we would say that the standard deviations are different. But if one is not more than twice the standard deviation of the other group, then we would feel comfortable sticking with the assumption that they're equal. And then what do we do from there? Well, then the calculation differs a little bit on how we calculate the number of standard errors that these two are apart. And that mainly differs based on what standard error we're going to use. So if they're similar, we pool the two groups. And instead of looking at it as the standard deviation of a group of 25 and a group of 25, we look at it as standard deviation of a group of 50. And we use that instead as the pooled standard deviation. Last week, if you go back, there's a formula. It's a little more complicated than that. You can go back and look at the formula for calculating the pooled standard deviation and then calculating what the standard error is. And if one is more than twice the other, then we assume that the variances, the standard deviations, are unequal, and we use a different calculation for the standard error. Right? So there's two ways we might calculate the standard error. Once we do that, we then say to ourselves, how many standard errors apart are these two? So if the standard error that we determine, whether it's pooled or not pooled, if the standard error that we find is equal to 1, or calculation says it's equal to 1, well then how many standard errors apart are these two values? Well, if the standard error is equal to 1, then 2.1 over 1 is equal to 2.1. So that's how many standard errors apart it is. If the standard error had been 2, well then these would only be 1.05 standard errors apart. Well, then what we would do at that point, we would say to ourselves, how many standard errors apart do we need to be in order to have less than 5% chance of being wrong if we reject the null hypothesis? And that's where our critical value of t comes in. We can go to the table and we can look up what our critical value of t is based on either pooled groups or unpooled groups. So for pooled, it would be 25 and 25 would be 50 minus 2 would be degrees of freedom is equal to 24. So I'm going to take a wild guess, and I'm going to say that our critical value of t is 2.06 or something like that. So in this case, 2.1, we would have exceeded our critical value. So we can say with less than 5% chance of being wrong that we can reject our null hypothesis and accept our alternative hypothesis. Okay, so great. So here I have wasted a whole bunch of time talking about reminding you how to do the t-test. Well, what has this got to do with analysis of variance? Why did I even bring this up? Okay, first of all, before I go any further, are you guys comfortable with that? Do you remember how we did this? And you can always go back to the previous session or two, and you can take a look at them again and take a look at the demonstration of how to calculate the t-values. equal variance is assumed, and so on and so forth, right? So equal variance is not assumed. So are we at least reasonably comfortable with that? I'll wait for a response. I know there's a little bit of a lag, so I hate to keep you waiting on this stuff, but I want to just make sure that I haven't completely lost you. I don't mind confusing you a little bit, but I don't want to confuse you so much that you get turned off. Okay, good. All right, so I'm going to move on from there. Okay, so now, where does this analysis variance comes in? Well, let's say, for instance, that now we're going to look at this again. We're going to measure the BMI, right? Again, same variable. That's a numerical variable, right? But now we're going to measure the BMI of, we're going to measure the numerical variable of, let's say, let me think of a few good groups that we might be interested for BMI. BMI of weightlifters, of people that do aerobic exercises, and people that do no exercise. Okay, so I'm going to go here. Let's say, okay, I'm going to do the same thing. I'm going to sample 25 weightlifters, 25 random weightlifters from this population, 25 people that are involved in aerobic exercises, and 25 people who don't do any exercise at all. So again, what am I going to wind up here? I'm going to wind up with the mean for weightlifters, the mean for sample mean, of course, that's what I'm looking for, the sample mean for people who do aerobic exercises, and the sample mean for people who do no exercise at all. Okay, so again, each one of these is going to have its own standard deviation. Standard deviation for weightlifters, the variability or another standard deviation for people who do aerobic exercises, and standard deviation for people who do no exercises. Okay, so now I could now just go ahead and do a t-test, right? So, I got means. I want to compare the means of two groups and so on. Well, t-test only works for two groups, right? So if I wanted to do this, I would have to do a t-test comparing weightlifters versus people who do weightlifters versus people who do aerobic exercise, weightlifters versus people who do no exercise, right? And I would have to do people who do aerobic exercise versus people who do no exercise, because they haven't been compared yet. Aerobic as compared to weightlifters, aerobic weightlifters, and people who do no exercise compared to these two groups. People who do aerobic compared to weightlifters and these. So at this point, I think everybody's been compared to everybody else. No, oh, wait a second, no exercise. Yeah, I think I got them. I think I got all of them. Yeah, okay. So problem here is I'm doing the t-test 3 times, right? And each time I do the t-test, what's my alpha error? What's my probability of being wrong that's acceptable to me? It's 0.05, right? Well, okay, that's 0.05 each time I run the t-test. So if I run the t-test 3 times, well, I've tripled my chances that I could be wrong if I reject the null hypothesis. Okay, not only that, what if I had said there weren't just 3 groups, right? Now there was also people that do yoga, people that do dance exercise, people that do that bicycle, right? Let's say now we have 6 groups. Well, now if I got 6 groups, if I want to use a t-test to compare the means of all these different groups, I'd have to compare weightlifters to aerobic exercise, weightlifters to no exercise, weightlifters to yoga, weightlifters to, I don't remember what that was, weightlifters to bicyclists, and so on and so forth, right? And then I would have to compare people do aerobic exercise to no exercise to yoga to whatever that is to this, and then no exercise to yoga to, and so on and so forth. So I would literally have to wind up running this test. I'm guessing 4, 5, 3, 2, 1, 4, 4. How many are there? 6, 5, 4, 3, 2, 1. Let's see. 3, 6, 10, 15 times. I have to run this 15 times. Well, 15 times, I run this 15 times. Number one, I've wasted a lot of time. And number two, if I look at it from the perspective of each time I run it, having that level of acceptable error, then there's a good shot that I'm going to be wrong on at least some of my conclusions, right? So this is unacceptable. I can't do this. When I have more than two groups, I need another method to analyze this. I need another method to compare these various groups against one another, the means of these various groups against one another. Okay, one that preserves my level of alpha error that I find acceptable, right? It doesn't just blow it up, right? Just preserves that so I can still be confident in that. And then number two, ideally, one that will do this all in one operation for me, so I don't have to do it over and over and over again. Okay, so how many any of you guys have read ahead and worked or done analysis of variance in another class, or remembered from remotely in the back of your minds from maybe an undergraduate class or something like that? I just want to know if this is like kind of new to you guys, completely new, or if this is something that you have even a distant memory of. Completely new. Okay, good. Well, that's a good thing. Yeah, now we know. Now we know there's a need for us to do this right here. Okay. Up until this point, we weren't sure, but now we're absolutely sure. Okay, good. All right. So what I would like to do now, I want to play that video that was the first video that I was talking about. And if you take a look at it, it's got a bunch of cherry trees on it. It's got my voice in the background. Now, there's two ways I can do this. I am going to pause recording, and I'm going to play this in this window. You'll be able to hear it. I won't be recording the video. You'll be able to hear it. Or you can just click on this link. It will open in another window, and you can pause. You can either, let's see, either minimize or, let's see, I'm trying to think of a way for you to be able to hear that background and have my noise in the background not work. Well, you got a choice. You can either watch it online, like with us. Okay, you'll see this one as soon as it starts playing. You know how long it is, and you can either watch it online as I play it, or you can drop out of GoToMeeting, watch the video. You'll be done about the same time that I'm done online, and then come back and I'll introduce the second video in whatever amount of time it is. I'm going to start it right now, and you can experiment with it. I'll give you an extra before I start talking again, I'll give an extra couple of minutes when we come back for the second video so you can decide how you're going to handle it. Okay, and so I'm going to give this a start. This week, we're going to use analysis of variance to compare means of them, except this time we're going to be looking at 3 or more groups.
This conference will now be recorded.
Okay, so we're back recording again. So what we've just learned is that analysis of variance takes advantage of the variability between the individual means of several groups, like the BMI groups that we looked at before. Okay, it looks at the individual means of them and looks to see how far apart are they, how variable are the means themselves, and then it looks at the variability within the groups themselves. So in other words, what that tells us is that if the means are close together, right? If the means, if the BMI of one group, BMI 23.4, 23.6, 23.7, if they're close together, right? It's hard to tell, it's hard to prove that those numbers are really different from one another. Okay, so it's better for us. It's easier for us to reject the null hypothesis. In other words, that mu1 is equal to mu2 is equal to mu3. It's easier for us to reject that null hypothesis if the means are far apart from one another. 21.0, 23.5, 26.7. Right? If they're far apart, it's easier for us to reject that null hypothesis. Well, the other player in this is our level of confidence that we really know what the mean is is tied into how variable the values are from that we got from the standard deviation for each group. So if the variability is very narrow, right, so the individual values don't vary very much from that mean, then again, it's easy to reject the null hypothesis. But if they vary a lot, right, if they vary a lot, there's so much overlap between the groups that it's harder to reject that null hypothesis that they're all equal. Okay, so in fact, it's good that we brought this up now, because now we've also broached the topic of what's the null hypothesis here. And the null hypothesis is that all of the means are equal to one another. mu1 is equal to mu2 is equal to mu3 is equal to mu4, and this could go on forever, like mu(n), for instance. Okay, you could have as many means as you wanted to, or came up with. Okay, so that's what our null hypothesis is. When we use analysis of variance, our alternative hypothesis is that we can say that with 95% certainty, less than 5% chance of being wrong, that this is not true, that we can reject this. Little complication here. When we do the analysis of variance, it doesn't mean that they're all different. All it means that at least one of the means is different from one of the other means. In other words, at least one of the means is different than one of the others, or in other words, that at least two of the means are not equal to one another. We don't know yet what those are, but at least two of the means are not equal to one another. Okay, so at least you could phrase it either way. At least two of the means are different from one another, or at least one of the means is different from the other means. At least one of the other means. So at least, I guess it's easier to just look at it that way. At least two of them are different. Okay, we don't know which two, right? But at least two of them are different. So that's analysis of variance, right? That's how we analyze the variance between the means and the variance within the groups in order to show that means are different from one another, or means are not different from one another. So hence, analysis of variance is really a method for comparing means. That's what this is all about. Dirty little secret. Okay, dirty little secret. If you do an analysis of variance on two groups, right? Normally we would do a t-test on two groups. But if you picked out the wrong analysis and you did an analysis of variance on two groups, you would get exactly the same result for the t-test as you get for analysis of variance. You would get exactly the same p-value, probability of being wrong if you reject the null hypothesis, right? Both of those would come out exactly the same as when doing the t-test. So secretly in the background, those two tests are really not that different, right? But we're gonna examine this further. So the next thing we might want to do is take a look at step by step, how might you actually analyze this? Okay, I'm gonna get rid of this, get this out of the way, and I'm going to, I think I already have it here somewhere. I'm gonna open up the file, ANOVA, oops, helps if it's spelled right, underscore Excel. I actually have a couple of them. One of them is with so you can see this one that's coming up in the background here. You can't read it probably, it's too small. Is actually the completed version of this, right? So you can have that. You can take a look at that if you want to try it on your own. A demo. Okay, let me see if I can't find it. Yeah, there we go. Here's a version of it. I'm going to open that up in Excel just so you can get a look at it before we play the video. I hate to bang on that like that. I know it's shocking to the ear, but that's the way the trackpad works. Alert. I don't know what that alert was, but I'll try this again, except this time I'm going to drag it to the desktop. Might be a little easier to open that way. Okay, oh yeah, it's working this time. Okay, so let's take a look at this thing. Data, actually this is the completed one. I don't want to give away the ranch yet. Okay, we'll get to that in a second. Demo, here's the demo version. Okay. Okay, let me improve the view here a little bit. Okay, so I'm starting with 3 groups. Let's say that this is some sort of exercise or test or something like that. And Fred is the boss of the first group. Jim is the boss of the second group, and Alice is the boss of the third group. This could just as easily be hospital 1, hospital 2, hospital 3, in terms of maybe admissions or number of accidents or something like that. Could be bridge number 1, bridge number 2, bridge number 3, number of accidents they had, or something of that nature. But it's just numerical variables. And I kept the numbers, the data set small, and the numbers very simple for that reason. So it's easy for us to work with. So if we were just comparing Jim to Fred, we would just do a t-test. We find the average of these 5 numbers, compare it to the average of these 5 numbers for Jim, and say the mean for Fred is equal to the mean for Jim. Well, things are complicated now because now we got Alice involved too. So we want to know if any of these means are different, right? So we would have to calculate mean for Jim, mean for Alice. I don't know, hypothesis would be the mean for Fred is equal to the mean for Jim is equal to the mean for Alice. And then we would want to know, are any of these means different from one another? Can we reject the idea that mean 1 equals mean 2 equals mean 3? Not necessarily identify right now which means are different. Okay, so I'm going to close this. This is the data set that we're working with. I'm going to close this, and then I'm going to play that second video. Okay, and I'm going to pause the recording while we play that second video.
This conference will now be recorded.
Okay, so I have various comments on this. I'm back, I'm here, and I'm confused. Okay, so that basically is the rundown on the response to that. I tried to go through that carefully and slowly. Now, one thing, the good news, the bad news is that, yeah, it's a kind of a complex calculation. It's not a difficult calculation. It's more of a torturous procedure because you have to calculate all these differences and the means and the sums of squares and so on and so forth. So it tends to be very tedious. And if you could imagine, if instead of 3 groups, we had 8 groups or 10 groups, right? It should be torture. We'd be here all day on Excel doing this, right? Fortunately, this may be the last time you'll ever have anyone will ever show you how to do it this way, and the last time that you even have to watch somebody do it this way or do it yourself this way. It's a nice exercise. If you get a chance just to kind of cement your knowledge, you might want to give it a try. There's on Blackboard, there's both the raw file, Excel file, with the data in it, and with the various boxes all ready for you to do your calculations. And there's a finished version of the calculations in a separate Excel file that you can click into and see the formulas that we use to fill in those boxes. Okay, so again, the good news is that you're not likely to have to repeat this unless you want to demonstrate it for yourself. From this point on, we're going to be using SPSS to do this, and it's going to be much simpler and much more direct. No, absolutely not. You don't have to do this every time. You never have to do this again if you're lucky, right? You're going to be using vertical software, statistical software, to do the calculation for analysis of variance. Okay, you may have some, perhaps, a masochistic professor in the future that might make you calculate it, but fortunately, most of us, manage to avoid that, right? So with the next video that we're going to we're going to do exactly the same calculation, same data set, same everything, except this time we're going to do it using SPSS. So we're going to go away again. I'm going to play I'm going to pause the recording and I'm going to play that video. And again, you can either watch it on the screen as I play it, or you can pause, drop out of GoToMeeting, and then come back again when you finish watching. And I'll wait a couple of minutes for you to get back on again when the video is done. So I'm going to pause, and then I'm going to start playing it again now.
This conference will now be recorded.
As I'm gonna wait a minute again still to see if anybody comes back, rejoins us and so on. I can probably see what we're doing here. Yeah, it looks like we're all back. So just to summarize, we did basically the same calculation. In fact, I just want to see if I can't just get to the point.
Repeat our analysis of variance using SPSS.
I want to get to
data squares.
Stop it right there. Okay, now, whoops. Oh my goodness.
The within group sum of squares, the degrees of freedom, divided one into the other to get the mean squares.
You probably can't see that this well,
but the numbers, the F score,
the numbers that we have here,
mean sum of squares between.
See, it's either sticks that thing in front of there, right where I don't want it. So I'll have to talk over the voice. But if you look in here very carefully, you'll know. Oh, it's working now. Okay, if you look in here very carefully, what do we have here? We have the sum of squares 17.2. We have within groups 25. Degrees of freedom, divide 17.2 by 2 gives us our 8 point whatever that was 9. Divide 25 by 12, it gives us our 2 point whatever, and so on and so on. So that is our mean sum of squares between the groups. Mean sum of squares between the groups. It's exactly the same number we calculated when we did Excel. So what's our F score going to be equal to? It's the mean sum of squares between the group, the sum of squares, mean sum of squares between the groups.
Groups divided by mean sum of squares.
Divided by the mean sum of squares within the groups. The variability between the means divided by the variability within the groups. Again, our 8 divided by 2 is the same as we had before, and it gives us that 4.095. Gives us the same result that we had before. The only difference here is, from when we ran it in Excel, is instead of taking that number and looking up a critical value of t, the way we had to do when we did it manually, SPSS actually calculates the exact probability of getting this big an F score if the means were, all of those means are equal to one another. So the chances of that happening is only 4%. That means that there's only 4% chance I would be wrong if I reject the idea that they're all equal, reject the null hypothesis, and accept the alternative hypothesis. At least 2 of these means are different from one another. Okay, can anybody tell me what are we missing now? You know, we can see how we can prove, we see how we can take the null hypothesis, mean 1 is equal to mean 2 is equal to mean 3 is equal to mean 4 is equal to mean 5 is equal to mean 6, and use SPSS to decide what probability there is that at least 2 of those means are different from one another, and if the chances of that happening, chances of being wrong if we reject that null hypothesis, all the means are equal, and accept the alternative hypothesis, chances of being wrong are less than 5%, then we go ahead and do it. We reject the null hypothesis. What's missing here? What part of this whole thing do we have we not dealt with here? Right? Can anybody guess what that might be? What are we missing here? Remember what I mentioned, something about post hoc tests? What do you think those post hoc tests might be for? Those after the fact tests. After the fact being, you would only run the tests if your null hypothesis was rejected. In other words, if alpha came out to be less than 0.05. What kind of test, what might we be looking for beyond what we've already proven when we reject the null hypothesis? Well, the alternative hypothesis, yeah, that at least 2 of the means are different, but a little bit more specific, what are we missing about this now? Which of the 2 means are different? Right, exactly right. Which of the 2 means are different? In other words, is mean 1 different from mean 3? Is mean 2 different from mean 5? Is mean 5 different from mean 2? Right, which of those means are different? This hasn't demonstrated that for us, right? It's only told us that at least 2 of the means are different. We need to know more than that. We need to know which of the means are different in order to proceed, so we understand what this data really is telling us. That's what the post hoc tests are about. That's why we run post hoc tests, right? So we're going to go ahead and run the post hoc tests. I'm going to do it on the recording here, but I'm also going to open the data up later on, so I can kind of annotate it as well. Okay, so we're going to part again, run the video, and then come back again afterwards. And again, keep in mind, we only run the post hoc tests when we've rejected the null hypothesis. If we fail to reject the null hypothesis, we say, oh, we haven't proven that the null hypothesis is not true. I can't reject the null hypothesis. So I'm left with mu1 is equal to mu2 is equal to mu3 is equal to 3. I haven't proved that they're equal, but I haven't proved that any of them are different. So that means I can't go on from that point. There's no point in running the post hoc tests if I can't even prove at least two of them are different from one another, if I can't reject the null hypothesis. Okay, so we're only going to proceed to the next step if we reject the null hypothesis. If our calculated F is more than the critical value of F, or if the p-value, the significance of our F value is less than 5%, less than 5% chance we'd be wrong to reject the null hypothesis. Okay, so we're going to go to the next video, which is to run the post hoc tests. And again, I'm going to pause recording.
This conference will now be recorded.
Okay, so we're back, and we completed a post hoc test. Now, I just want to go through, I just want to kind of take a look at this with you, and I'm going to open up the file in a second, but I just want to go through the recording.
Or p-value less than
Go
only
here.
perform these tests.
I wonder if I can turn down that and still have you hear me. Yes, I can. Oh, okay, that works good. Okay, so if I look at this post hoc test, and so I can do this without getting that annoying thing in the background. Let's get rid of that. Okay, this post hoc test, what SPSS winds up doing is that instead of comparing all of the groups against one another, as we would for our primary analysis of variance, now it actually goes back and re-examines our results and compares individually. It compares Fred to Joe, Fred to Alice, Fred to Jim rather, Fred to Alice, Jim to Alice, so that all of the combinations are covered here. It actually does them twice. If you notice, it does Fred and Jim, but then it does Jim and Fred. So it's actually doing them twice. And if you look at the numbers that you actually get, they actually wind up being repeated as well. So it's not like you get different values there. Like that. Okay, let me get back to that. It's not like you get different values, like 3.19 and 3.19, the same analysis, you wind up with the same result. So the only comparison that is less than 5% is Fred and Alice. So that's the only one that we have enough evidence for to say that the mean value for Alice is different from the mean value for Fred. In other words, reject the null hypothesis that Fred and Alice have the same average, and that we reject that, and we accept the alternative hypothesis that their averages are different, their means are different from one another. Okay, and that's what those post hoc tests were. And you might have noticed, I'm gonna actually stop this. I'm gonna open up that file in SPSS. Okay, let me get back to the data set here. Actually, it's just easier for me to take this and SPSS, and variance, here it is. Here's the SPSS version of it. I'm going to put it on my desktop, make it a little easier. Okay, and I'm going to open SPSS and open that data file. Bounce, bounce, bounce. Okay, open data file. And I need to go to my desktop to find it. And let's see, there it is. Oops, I missed going to my desktop there. Something bad happened. Where is my desktop? Okay, and here's our data file here, SPSS demo for ANOVA. Okay, SPSS opens it. Notice again that there's two variables here. There's the there's the categorical variable group, which we know, I'm going to go click on view and select value labels. We know that we've identified those in the variable view as 1 being Fred, 2 being data from Jim, and 3 being data from Alice. And this is numerical data. And you want to know something, it actually should say scalar instead of, but it doesn't really matter. It worked out anyway because it recognizes it as some kind of numerical data. Okay, so at any rate, so now when we ran our analysis of variance, we just did this and analyze. Now, because what we're really doing here, even though it's an analysis of variance, we're looking at variances. What we're really doing here is we're comparing the means of the groups, of many groups, rather than just 2. We're going to go past one sample t-test, past independent samples t-test, and other methods of comparing means of groups, past paired samples t-test, all the way to one-way analysis of variance. And we're at the point now we can identify, well, the variable, the numerical variable, which is going to represent our means is called measurement, and the groups that we've got it divided up into, that we want to factor it into, in other words, break it up into 3 groups. Those groups are Jim, Fred, and Alice. I'm going to move that in here. We can do our analysis, okay, and again, until you've determined that you can reject the null hypothesis, the p-value is less than 0.05, you don't proceed to your post-hoc test. So if this is bigger than 0.05, we're done. We failed to reject the null hypothesis. If I go to analyze now, I'm going to repeat this exactly the same way. Analyze, compare means, one-way analysis of variance. And now, instead of going and doing the calculation, going directly and doing the calculation, I'm going to go into post-hoc. Post-hoc again means after the fact, after we've successfully rejected the null hypothesis. Let's take a closer look at this. Let's compare the means for each one of these different groups to one another, which might be, in this case, 3 comparisons. But if we had 5 variables, it might be 15 comparisons. If we had 20 variables, it might be 19 plus 18, and so on and so forth. Many, many, many different comparisons. Well, there are many different choices that we can use in order to calculate our post-hoc test to compare these individual groups. Okay, the most common ones that you'll typically see. And there's reasons, you know, that for our purposes we don't have to be that concerned about. But the ones that we would be most likely to use are probably least square as LSD, Bonferroni, or Tukey. All of these are relatively conservative tests that will, if anything, maybe slightly underestimate your chances of rejecting a null hypothesis rather than overestimating. So pretty conservative. So we would probably use those. I'm going to use Bonferroni. That's the one I would pick most typically. But if you use Tukey, that would be fine. Or LSD at least square, that would be fine too. Now, we have this opportunity to define what our level of significance is. What's our acceptable level of error, our alpha error. We could change that to 0.05. We could leave it as 0.05, or we could change it to 0.01 if we want to be 99% certain that that we can reject the null hypothesis. Or in other words, less than 1 chance of being wrong. If we reject the null hypothesis, we would change that to 0.01. Okay, we're going to leave it 0.05 for now. So I'm going to click continue, and then OK. And it will repeat the analysis of variance. We got the same result again, and then give us a separate table. And in this separate table, we can see the exact probability that we would be wrong if we reject the null hypothesis for just comparing Fred and Jim or Jim and Alice and so on and so forth. And it does it twice. So you'll notice that there is only one instance here where this number is less than 0.0. There's only two places where it's less than 0.05. That's 0.045. Okay, and that occurs in actually the same analysis. That's Fred versus Alice and Alice versus Fred, right? So it's really the same result. The rest of the results are all greater than 0.05. So we cannot say that those means are different from one another. Okay, and if you look down here, you look over here, asterisk, the mean difference is significant at the 0.05 level. Well, let's see where you see that asterisk. There's an asterisk right there. That's Fred and Alice. So it highlights for you, right? It's a little hard for you guys to see, but it highlights for you that that analysis resulted in a significant difference, right? And again, here's the asterisk down here when it's repeated and so on and so forth. Had we changed that to 0.01, none of these would have had the asterisk. None of these would have been less than 0.01, right? So since they weren't less than 0.01, if we wanted 1% chance of being wrong, well, then we would have, we would not even gotten to this point. Because if we had said back with analysis of variance that we wanted to be that certain, then we wouldn't have even run the post-hoc test. But we would have seen that with post-hoc test when we tried to run it anyway. Okay, so let me pause here for a second and ask you guys, how do you feel about this? Do you have any questions right now? You might need to mull this over, think it over, maybe try a homework assignment and so on and so forth. Right now, I had posted the homework assignment for Ttest for single sample Ttest and independent samples Ttest. Okay, so how do you guys feel about this? Give me a little bit of feedback. It's not impossible, right? It's not that hard to understand. And using SPSS makes this a much simpler process than having to calculate it by hand. And that's probably true of anything we're going to wind up doing. So where would we use this again? We would use this when we are comparing the means of more than two groups. If we're comparing the means of two groups, we don't need analysis of variance. We have a perfectly good tool for that, and that's the Ttest. So this is really an extension of the Ttest, where we can compare multiple means at the same time. If we were successful in rejecting null hypothesis and accepting the alternative hypothesis, at least two of the means, not all of them, but at least two of the means are different, well, then we can go ahead and run that additional analysis, okay, for that post hoc test. So Fred analysis means are the ones, oops, let me read that are different. Yes, exactly right. Fred and Alice, well, they're all different. All the means are different, right? And that happens all the time. If we take an average, one group and another group, they're all going to be different. But Fred analysis is the ones that we can say with less than 5% chance of being wrong are statistically significantly different. In other words, the actual population means where we'd be less than 5% chance of being wrong if we said the actual population means are different from one another, right? So yes, you got that, you interpreted that correctly. Okay, just need to practice it. Yeah, okay, good. I think I gave you another data set here. Okay, so what I'd like to do now is take a break for about maybe 10 or 15 minutes, come back at 7:15, and we're gonna move on. I'll do a brief PowerPoint, I'll run through the PowerPoint quickly, and then from there, I think I have another data set that we can just play around with this. Okay, so, take a break, have coffee, eat a little dinner, have a cocktail, don't have two cocktails, and come back at 7:15 and we'll resume this. Okay, guys?
This conference will now be recorded.
Okay, so let's take a look at this again. I'm going to play this full screen, so I won't be able to see your comments for a few moments, but I'll drop out and stop my slides for about maybe 5 or 10 slides in and just check, see if there's some questions or comments at that point. So I'm going to go ahead and play, start. And one-way analysis of variance. So what we're looking at here is to understand why we're using this technique. Why are we just not staying with the t-test, which perfectly serves us perfectly well for comparing means, okay, and what the assumptions are when we take this test, so we make sure that we stay within those assumptions so that we don't violate any of the rules and wind up assuming that we've proven something when we haven't really proven something. How to carry out the tests, how to interpret the table that we produce when we carry out the test in SPSS, and then when and how we would carry out post hoc tests for situations where we want to look at individual comparisons of means rather than several means at the same time. So remember, analysis of variance, we're comparing the means of different groups, okay? And it's different because the number of groups we're comparing is more than two. If it's just two, we would use the t-test, various versions of the t-test, single sample, independent sample, paired sample, and so on. Independent sample with equal variances, independent sample with unequal variances, and so on. In this case, we're examining more than two groups at the same time. And then we have to carry out these. Once we have rejected our null hypothesis, then we have to carry out post hoc tests to further examine our data. So we're going to take a look at this. Okay, so t-test. What is a t-test trying to show us? It's trying to show us that we can demonstrate that there's a statistically significant difference. In other words, we can say with a small level of error, possibility of error, that means the two groups are different from one another. When we don't know what the means of the two groups are, but our only insight into that is the mean and the variability of samples that we've taken from those two groups, okay, of various sizes. So here is a cell phone study, a mean response time. One is 585 milliseconds, the other is 535 milliseconds. It was very nice that the average for our samples were that different, but can we extrapolate that to the means of all of the cell phone response times for those carriers? Right, and we can see what we've done here is we've plotted a box plot. We're going to do that on the next set of data when we're done with this. And that box plot allows us to examine where's the middle of these samples, and how far apart is the middle of these samples, and how variable are the individual values in these. So we can see that although we don't have the mean, we have the median indicated here in the middle, right? We can see that the medians are different from one another, right? It's kind of a substitute for the mean in this case. So we can see that the middles are different from one another, but look, there's so much variability in both of these that there's so much overlap. It's really hard to tell whether our sample is really representative of these two populations. It would have been much better if these box plots were further apart. Okay, so let's take an example here. Okay, here's we're evaluating training methods, 3 different training methods, and this is the students' performance after going through these 3 training methods. These 9 students altogether, each one of them had taken a different method of training, and this is a result of their scores. So we examined the means. The means of method 1 was 12, learning time is 12 minutes. The mean for method 2 is 10 minutes, and the mean for method 3 is 22 minutes. One thing I notice is that the standard deviations are pretty similar. You see the red box over there. The standard deviations here are pretty similar. Okay. On the other hand, though, the means are, there's different cases here, right? The mean for method 1 is 12. The mean for method 2 is 10. They're not very different. However, method 3 takes 22 minutes of learning time, and that's quite different from method 1 and method 2. So even though we've only sampled 3 students trained in each method, we're starting to see that it looks like method 1 and method 2 is going to be hard for us to say that the means are really different given this is such a small sample, right? But method 3, boy, it's looking more and more like method 3 is significantly different than method 1 and method 2. Okay, and here it is presented as a box plot. Method 1 and method 2, the means are not very different from one another, and there's a lot of overlap between them. And method 3 is quite different. It's much different than the means for the other two groups, and the variability is such that there isn't much overlap between that sample's values and the method 1 and method 2's values. So gee, that really looks like kind of situation where we would be able to say that the mean for method 1, mu1, equals mu2 equals mu3 is our null hypothesis, that we can reject that null hypothesis because method 3 looks to be so much different. Now, once we reject that null hypothesis, we might want to go back and take another look and say to ourselves, well, you know, I can't really say mu1 and mu2 are different from one another, but it sure does look like mu3 is different from mu1 and mu3 is different from mu2. Population means for mu3 are different from the means for the other two groups. Okay, so why not use t-tests? We kind of introduced that before when we were going through our examples, didn't we? And we determined that the problem there is that each time we run a t-test, we're accepting 5% chance of being wrong, of creating a type 1 error, which is when we reject the null hypothesis, when it's true, okay, when the means are equal, okay, means the populations are equal. And that's kind of error that we don't want to make, because that's kind of error that would suggest that a drug worked, that an intervention was good, that we should spend money on something, invest time and energy on pursuing that, and so on and so forth. We don't want that to happen. So alpha errors are not good for us. Okay, so if we do a single t-test, each time we do it, it's 5% risk. However, if we repeat that test over and over and over again, like in this case, even for 3, well, then it's almost 15% chance that we would be wrong if we reject the null hypothesis using the same criteria, using that 5% each time we try it criteria. Okay. So basic idea of analysis of variance. When there's a lot of variability within the groups and the means are not different enough, it's hard to tell that the means of the populations are different. That's what we see on the left-hand side. When the means are different from one another, but the variability within the groups is small, it becomes much easier to prove statistically that the population means are likely to be different from one another as well. So that's what those box plots do for us as well. Okay, and again, here's another way of showing that this group 3, the variability for group 3, that doesn't have much overlap with the variability within group 1 and group 2. But they, compared to each other, there's a lot of overlap between the two of them. So that would suggest that it would be very easy for the difference in means to just simply be between mu1 and mu2, to just simply be due to sampling differences, sampling error. But it sure looks like the difference from mu3 from those first two has some real reason, perhaps that the population for group 3 really is different than the population for group 1 and 2. Okay, again, you keep seeing here, as we have in the past, that the means are means. When we talk about population, we call that the values, the descriptive statistics for population, we call them parameters. And the parameters for the population, the center, is the mean, mu1, mu2, etc. And the parameter for standard deviation is indicated as sigma. Okay, parameter means population, and we use Greek letters mu and sigma. When we calculate sample statistics, the mean of a sample is indicated by x bar, and the standard deviation of a sample is indicated by S or by SD or something of that nature. The standard deviation of a sample distribution, different, right? Okay, but we know that. Okay, one-way analysis of variance. What's our null and alternative hypothesis when we do this? Let me just pause for a second. Go back here so I can see the screen, whole screen. And let me ask you guys okay with this so far? You can see my screen when I play it full screen, right? You can hear me and see my screen? Okay, good. Thank you very much. Okay, good. Excellent. Okay, any questions so far? I mean, we're rehashing basically the same stuff we discussed. Good. Excellent. Okay, I'm going to pick up from where I left off. Okay, so what's our null alternative hypothesis when we use this new tool called analysis of variance? Okay, so number one, when we were doing a single sample t-test, right, our null hypothesis was mu is equal to some known value for mu. So it's indicated here as mu0, but you could equally just put in the value. Mu is equal to 110. And our alternative hypothesis is that mu is not equal to 110. When we're looking at independent samples t-test, two sample t-tests, or one-way analysis of variance, let's ignore that second part of that, or one-way analysis of variance. When we're looking at two populations, two samples, right? Our null hypothesis is that the mean the mean of the population that the first sample of the first group we sampled is equal to the mean of the second population. And our alternative hypothesis is that the means of the two populations are different. Notice we never talk about, in null hypothesis, we never talk about X bar. We're always talking about the population means. The sample is a way for us to get to that point, right? X bar and S, they're a way for us to get to that point. But the real null hypothesis is our predictions about the true population mean, which is really what we're always interested in. Okay, now, again, remember that dirty little secret I told you before, that if we run a one-way analysis of variance, if we calculate the analysis of variance in SPSS using only two groups, we could actually run analysis of variance on just two groups, right? We wouldn't want to run a t-test on more than two groups, but we can run analysis of variance on only two groups. The result, the p-value, the probability that we would get that extreme of value, or the probability that we would be wrong if we reject the null hypothesis, is exactly the same when we run analysis of variance as if we had run the t-test on the same data. Okay, so you could actually do that if you in a pinch, but actually usually run the t-test. Now, the place where analysis of variance really shines, really helps us out, is when we're comparing the means of multiple populations at the same time, to enable us to do that calculation without running multiple t-tests, each one of them that could introduce additional error. So our null hypothesis for that is the mu for that mean for group 1 mu is equal to the mu for group 2 is equal to mu for group 3, and so on and so forth, where the number of groups is equal to or greater than 3. Okay, yeah, so normally we'd only use it for when we are looking at groups of three different groups or more. Ethnicities, for instance, you might have 8 ethnicities, or in New York City you could have 40 ethnicities or 50 ethnicities or even more, right? If you want to compare them all at the same time, that's something that wouldn't be practical with t-test. Okay, so the alternative hypothesis is not all population means are identical. Okay, so that means that two of those are different from one another. In other words, at least two of those are different from one another. At this stage, when we first run analysis of variance, we don't know which two, just that two are different. Okay, so what are the assumptions? Okay, first of all, that the data is drawn from populations that are roughly normally distributed, or that the sample size is large. Now you can deal with it, it's robust. Analysis of variance is robust, meaning that if the sample size is large, you're not so dependent on a normal distribution, a perfectly normal distribution. Larger the sample sizes are, the less concern you have about the normality of the distribution. Same is true of the t-test, if you recall. Once you get over 30 or 40, the central limit theorem tells us, well, it doesn't, the samples, repeated samples from the same population wind up being normally distributed, even though the original population may not be perfectly normally distributed. Okay, and that's a property of repeated sample means, right? So and then for that to be true, the larger sample size, the more reliable that is. And as a rough guesstimate, you want sample size at least 30 or 40 if you have a population that may be skewed a little bit. Okay, one-way analysis group with 3 groups is generally safe when the sum of the subjects in the 3 groups is greater than 15. In other words, if you have less than 15, I think that it's not quite so reliable. Okay, or if the sample, if the number of people, the sample sizes is between 15 and 40, if the original populations are moderately skewed, and there's no more than 3 outliers, or if the sum of all your the sum of the samples you have is 40, sample size you have is greater than 40, then even with skewed data and a few outliers, you can depend on analysis of variance to work pretty well. Okay, so the sample size makes you more comfortable whether the original populations are normally distributed or not normally distributed. Homoscedasticity. Let me repeat that. Homoscedasticity means equal standard deviation. So this test, one of the assumptions of this test is that the populations that these are drawn from are approximately equal, not perfectly equal, but approximately equal. Okay, because we're so dependent on this interaction between the variability between the means and within the individual groups. Okay, so what do we mean approximately equal? Okay, well, again, just like we did with the T-test when we talked about equal variances or unequal variance, as long as they're not, one is not double what the others are, then we can be relatively confident that the analysis of variance will work out pretty well. We also have to make sure that when we take a sample, that it's truly an independent sample, and that these subjects are not related in some way or not skewed, and so on and so forth. So that they're drawn from the various populations of 3 or 4 or 5 populations, and that they're randomly assigned to the separate groups. Okay, so here's our calculation for the variability, the variance, the mean squares within the groups and between the groups. Okay, and it's laid out a little bit differently than we did before, but it's really basically the same thing. Here's a variability times n minus 1, and so on and so forth. We did this up in the upper right-hand corner of the Excel sheet, and we divided by the degrees of freedom. In our case, it was 15 minus 3 was 12. And between the groups, this is our these are the difference between the individual means and the values, and then we squared the differences, and then we added them all together and divided by the degrees of freedom. Okay, which was again that was our sum of all of those. Actually, that's number of groups, and 3 groups minus 1 is 2, and this was our number of groups. Actually, it's number of samples. We had to write. This is number of groups 2 minus 1. Okay, so but basically the same thing. This is an illustration of the exercise that we did just a few moments ago using Excel, and then repeated using SPSS. Okay, total variability. Okay, so between groups variability and within groups variability. In other words, how different are the means and how much variability is within the groups. So we want this variability between the groups, variability between the groups, in other words, between the means. We want this number here between the groups, the means, to be large. We want that difference between the means to be large. And we want the difference within the groups, the variability within the groups down here, to be small. So when you have a big numerator and a small denominator, as the numerator gets larger, difference between the means gets larger, that makes the F statistic larger. As this number gets smaller, the variability within the groups gets smaller, then we're dividing this by a smaller number. So again, it makes the F statistic to be a larger number. So we want this to be big and this to be small. So we get a nice large F statistic. Okay, now when we calculate our F statistic, for each sample size and a number of groups and so on and so forth, we have a different chart for our F statistic. And we summarize it in a table, just like the T values, by indicating the number of degrees of freedom between the groups, with a number of degrees of freedom between the groups in our columns, and the number of samples in our horizontal rows. And again, we illustrated that in our lab video. And you find the intersection, and that gives you a critical value of F. A value of F that's far enough over to the right here that you have only this area that's a percentage that you would be likely to get that if the null hypothesis were true. In other words, this area is, we want that area to be less than 5%. So we want to exceed the critical value of F for the analysis that we're doing, for the number of degrees of freedom between the groups and number of degrees of freedom within the groups. Okay, and here's an example of this. Here's our alpha, right? This is 5%. In other words, we want F to be big enough that there's only 5% of the distribution is left here. So this is 5%. And the p-value from SPSS is smaller than that. So in other words, this might represent 5% to right here, and then our p-value might represent 3%. So our p-value is less than alpha. It's 3%. It's at the 3% point on the F distribution, and alpha is the 5% point. So our p-value is less than 5%, so we can reject the null hypothesis. Okay, again, here's another look at this, the variability and the difference between the means and how we might look at that. Okay, here's the table from SPSS for this specific analysis. Let's take a look at these numbers a little bit more carefully. If I look at these are the variability, the sum of squares between the groups. And then between the groups, there's 3 groups, -1 is 2 degrees of freedom. So the sum of squares between the groups is 248 divided by degrees of freedom. The mean sum of squares, or the average sum of squares, is 124. That's what showed as our S squared before. And within the groups, the sum of squares is 66, and there were 3 groups with 3 people in each group. There were total of 9 people that were sampled, and -3 for the number of groups, 9 minus 3, the degrees of freedom is 6. 66 divided by 6 is 11. So 124 divided by 11 is 11.273. That is how we get our F score. It's the mean sum of squares between the groups divided by the mean sum of squares within the groups. I could literally say on a test, I might be able to leave one of these numbers out, and you would be able to figure it out from what's missing here, from the other numbers that are still behind. So we know that now we got 2 degrees of freedom and 6 degrees of freedom. We could go to our table to look up what our critical value of F is. And I'm just going to make a number up. I'm going to say our critical value F turns out to be 5. Well, the F score that we've calculated is way bigger than 5. So that would be an indication where we can reject our null hypothesis. SPSS doesn't bother to calculate the critical value of F. It goes right past that stuff and just tells us what's the probability we would be wrong if we reject the null hypothesis. A real statistician's way of describing this is what's the probability that we would get such a difference between the means with this variability within the groups. What's the likelihood we would get that big a difference if the null hypothesis were true? And that would only occur less than 1% of the time. So it would occur infrequently enough that we could come to the conclusion that that our null hypothesis is not true and we can reject it. Okay, another way, if you want to look at it a little bit more simply, you might be able to say that, and this is not exactly the way a statistician would describe this, but from a practical standpoint, you might be able to say, well, what's the probability I'd be wrong if I reject the null hypothesis? Well, again, less than 1%. So you can reject the null hypothesis and be confident there's only a 1% chance you would be wrong, which satisfies your alpha error. You're willing to reject the null hypothesis as long as the chances of being wrong is less than 5%. And that you've accomplished here, so you can go ahead and do that. Okay. So let me try and get this to the next slide here. Okay, yep, you can step through that if you want on your own. Okay, and there it is. Okay, so now, again, just as we examined before when we did the examples, right? That tells you that at least two of these means are different from one another, right? But it doesn't tell you which of the means are different from one another. Hence the necessity in SPSS for doing the post-hoc test. Okay, how do we get this output? Analyze, compare means, one-way analysis of variance. Then we take the quantitative variable and move it into the dependent list. That could be BMI, that could be, in this case, learning time, could be weight, could be heart rate, could be blood pressure, any numerical variable. And then we take the nominal grouping variable, right, which in this case was, I forget what it was, the learning method, method 1, method 2, method 3, right? We move that nominal variable, right, that's three groups, we move that into the factor. We want the means broken up by which group they are, which nominal group they are, method 1, method 2, and method 3. And then we go ahead and run our analysis of variance, and we go ahead and run our analysis of variance, and we get our results. And our F-score is large enough to give us a p-value less than 0.05. We reject our null hypothesis, and at that point, we go and we run the post-hoc test. Tukey, Bonferroni, those are the two I would probably, one of those two. You should get same results in terms of what you might reject or not reject if you want, if you were at that point. So you would run your post-hoc test, and then examine the results to see which of the comparisons of group 1 to group 2, group 1 to group 3, group 1 to group 4, group 2 to group 3, so on and so forth, which of those has a significance level, a p-value less than 0.05, and those are the ones that you're going to accept the alternative that the true population means for those samples groups are different from one another. Okay, it's always nice to plot the box plot because box plot is going to help you examine that, see that a little bit more clearly, or anticipate it a little bit better. Okay, the p-test, the f-test has a small p-value. The analysis but it has a small p-value. The test does not specify which means are different or how different they really are. Even though you can reject the null hypothesis for analysis of variance, you still at that point don't know which of the means are different from one another. Okay, you can look at the box plots and or create confidence intervals to get an idea of which ones of these might be different from one another, but you can also just calculate the post-hoc test and get a quantitative result for which of these means are different from one another. Now, what if your null hypothesis, if your analysis of variance comes up with an F-value of 2.8, which is smaller than your critical value, and a significance of 0.09, which is 9% is greater than 5%, 0.05, you fail to reject the null hypothesis. Well, then you don't run the post-hoc test. You don't roll the dice and run the post-hoc test. You only run the post-hoc test if the F-test is significant, and if the alpha, the p-value, the significance for the F-test is less than 0.05. Yeah, if you were referring to the one that we just saw in the previous slide, yes, you would reject the null hypothesis. and accept the alternative hypothesis, but then you would run the Posthoc test. Okay, Bonferroni, apply to any pre-planned estimate, contrast, use it for any design, cannot be used for data snooping, which means to choose the contrast that the data seems to suggest. Tukey, it's good for pairwise comparisons, and a couple of the other methods. So for our purposes, Bonferroni and Tukey are perfectly adequate for almost anything that we would want to do. Okay, confidence interval, comparing pairs of means. When confidence interval does not contain 0, we can infer that the population means are different. And this is just like as we did before, instead of looking at it from the perspective when we have paired samples, instead of looking at it from the perspective of the means are different from one another, we look at the differences for the differences, we examine whether the differences in the means are equal to 0 or not equal to 0. I don't want to make this too complicated, so don't worry about that particular slide. So now here's our Posthoc test. And here's a situation where we're comparing method 1 to method 2 to method 3. And again, it does it twice, does every permutation of it. So it does it twice. But look, we have, well, because we checked off mean differences significance at 0.05 level when we were doing the analysis, right? It actually gives us an asterisk next to the comparisons that are statistically significant. So in this case, method 1 is not apparently significantly different than method 2. Look at how high that significance is, way bigger than 0.05. But it is statistically different from method 3. So method 1 and method 3 are different, less than 5% chance. How about method 2 and method 3? Well, again, statistically significant. See, method 3, method 2, same analysis just comes up again. This is the same analysis comes up again. So it sure looks like method 3 is the oddball one here, right? Method 3 is different than method 2, and method 3 is statistically different from method 1. So I wonder what that would look like if I created box plots. Well, in fact, this is what it looks like. Let me see if we can get a look at that. I got something in my way here, so I need to move that so I can talk about it. So here, take a look. Here's the box plot that shows you that the mean value or the median value for method 3 is way up here, and that's the variability. And it's easy to tell that method 3 is different from these other two methods, but harder to tell or to prove that the two of these are different. And based on our sample size, we were unsuccessful at saying that these two are different, but we were successful at rejecting the null hypothesis that method 3 equals method 1 and that method 3 equals method 2. Those we were able to distinguish pretty easily. But the other two, sample size just wasn't big enough for us to tell for sure. So we don't reject that. We don't reject the null hypothesis that those two might be equal. Okay, let me get back to this. Let's see if I can't get it to advance. There we go. Okay. Okay, so I'm going to summarize all this. Okay, we use the F-test to test the null hypothesis that 2 or more groups have identical means. Really, I would stretch that to 3 because you'd probably stick with the T-test if you were. But 2 or more, you know it works for 2, so you could use it for 2, right, conceivably. Usually you're applying it when you're comparing the means of 3 or more tests rather than just 2. Chi-square statistic, we didn't talk about that yet, so I wouldn't worry about this particular comment at this stage. Okay, next week, well, maybe I'll introduce it on Wednesday, but for right now, the chi-square statistic, I'm going to say that we're not so sure about that yet. Okay, so we'll play with that later on. Okay, meaning the statement that the F statistic is right skewed and always positive just describes that unlike the normal distribution where you have a bell-shaped curve, the mean is in the middle and half of it is negative and half of it is positive, right? The z-scores, right? With the F statistic, It starts out at 0, goes up, comes down. It's always positive. It's always on the right side of the axis. And number 2, it's right skewed. It goes all the way out and gets narrower and narrower, but goes further out. So the appearance of it is right skewed. In other words, the areas get smaller and smaller as you go further out. Okay, so just that's the shape of it. So I wouldn't worry about it past that point. Okay, normally distributed population, heteroscedasticity, and independent samples are your assumptions. And only use the post-hoc test if your F-test is significant, if your analysis of variance is statistically significant, p-value less than 0.05, then go ahead with the post-hoc test. But if it isn't, don't do the post-hoc test. You just simply fail to reject your null hypothesis. And I think, okay, let me get to that. I think that's the end of that PowerPoint. Okay, so I'm going to call it a night. I think we've beaten this to death pretty well. And I'm thinking of, I don't think anybody in their right mind is coming in here on Wednesday night just before the 4th of July. So I am going to have, at our usual class time, 5:30, I'm going to do a review session. I won't introduce anything new on Wednesday. I'm just going to review the Ttest and analysis of variance. And maybe I'll do a little introduce a little tickle of chi-square, but we'll work on chi-square on Monday in earnest. We're a little bit ahead of the syllabus, so I think we can afford to do that. So do not come into here on Wednesday. Just strictly, we'll strictly do this online. I'm presuming that, right? All right, you guys, I'm here just in case you don't realize it. I am literally here alone talking to myself. Even the guy that you guys have been here a few times, even that guy that kind of hangs out in the back over here and works on the computer, that doesn't listen to us at all, even he left. So I'm completely here by myself. So I'm presuming that what that means is that because it's a holiday week, that you're not likely to want to come in on Wednesday. So I'm going to assume that we're going to do a review session on Wednesday online, and I'll record it. Yeah, I'll record the review session and then post it afterwards. And also this will be posted as well. And you'll have on the recording, you'll have all the parts of this that do not include the video. The videos you can always play separately. So I didn't record the portions of it where I did the video. I don't think that would work all that well on the recording part of this. And I think it's easier to just look at them separately anyway, especially when you're at home and just need to open just another window. Okay, so I hope that's, I hope I haven't confused you guys. I hope I presented this as simply and as clearly as possible. Okay, and I will post a homework for analysis of variance. It won't be due until after the holiday weekend, so you won't have to worry about that too much. And again, all you gotta do is make a first effort at it, and as long as you submit something, anything basically, just so you've looked at it and said to yourself, this is what I need to be doing. So you'll be able to go back anytime during the remainder of the semester to improve your score in it. Okay, again, this is meant to keep you and so on, keep you. Okay, good. Like I said, I'll record the session. It'll be a review session, and I'll post on Blackboard. I will post a discussions group where if you have a specific question you want to bring up, even on the homework or something like that, if you want me to review a homework problem or something like that, I'll be glad to do that. And just post it on the location on the discussions board, where later on tonight, not right now, but later on tonight, I will create a thread for exactly that. I'll make sure to cover it on Wednesday night. And if you're shy, you can always email me. If you email me, just make sure you put PH750 into the subject line. So my email program captures it and doesn't send it to spam or something like that. So have a good night. And if this last time we're talking until the holiday, have a great holiday. Don't play with fireworks. We don't want you getting hurt and stuff like that. Don't play with fireworks. Just watch the professionals, right? As they used to tell me when I was a kid. And trust me, I got injured a couple of times with fireworks. Okay. If you didn't do well with your first assignment, just redo it. Just, you can go back and do it again. The only thing with the first assignment is that in order for it doesn't auto grade, because part of the first assignment is you have to upload a document, which I have to read to grade. Okay, so it doesn't grade it automatically. The thing is that a lot of people put a lot of upload a lot of versions of it. So I only grade the ones that are the last ones, because I need to have a life. There's that many of them. But the problem with that is that if you were to do it again, I would see your previous score, but and that there are ungraded versions, but I would not know that the ungraded version is one that you submitted after that, the one that I graded. So you might want to just drop me an email, let me know, Tony, I submitted a new version of assignment number 1, so I know to go back there and grade it. Okay? So yeah, any of these assignments, the homework is intended for you to use as a tool to learn this. It's not intended, and it's also means that when you go back and you get your score up to as high as you can on this, it's entirely conceivable that you could get 100% on that portion of the exam, of the course, which is, I don't remember, you have to look at the syllabus, but it's like 30 or 40% of the course grade is based on the homework. So it'll really help out to do those homeworks and go back and complete them and make sure you do them right. If you stumbled on an exam, that goes a long way to making up for an exam stumble. Okay, so good night, guys. Again, have a great weekend. Bye.